everyone. This video is about tables. Now, before we get started, I wanted to let you know that there is a set of videos that are about tables that were already created last semester. And this is sort of just adding on to that, but it's the first video. The later videos may refer to an assignment, but because it was recorded last semester, the assignment is not relevant for the current semester. So just keep that in mind. Otherwise, the material is still relevant for what we're studying. So let's get started. So a table is effectively another abstract data type. So it's like a list is an abstract data type. Remember, we started talking about this when we started talking about linked lists. There's an idea of a list, and a list you can implement it with an array, or you can implement it with a linked list, right? So an abstract data type defines a set of operations without defining its underlying data structure. Okay, without defining the the way that you're going to actually store the data. So tables are similar. They define a series of operations that you can do, but they do not actually define the underlying data structure itself. So in this first video, we're going to actually take a look at an introduction to how tables work, what they are, and then take a look at a very simple representation of this particular data type. Now, it's going to be somewhat interactive, so I'm going to be showing you like what some of the things to watch out for are and think about how you might implement something like this. But let's get started in any case. So a table is an abstract data type, and really what it is it defines a collection of key value pairs. Okay, so key value pairs are the key. Now, a key value pair is sometimes called a record. So you might hear about, you might say key value pair, or you might, for a shorter word, you might say record, but effectively they are the same thing. A record is a key value pair. Now, now this collection um, is not ordered. So that is one of the key differences. So in a list, there is a distinct idea of this is the very first thing in the list. This is the second thing in the list. This is the third thing in the list. There's a distinct ordering to everything that is in a list. In a table, key value pairs are not ordered. They are simply part of a collection. Now, within the same collection, keys, each key is unique within the collection. So this is really, really important. The idea that a key is not is there's only going to be one of each key within the same collection. So that is really, really important because it is effectively the key identifies the record. Okay, so every single record has a key and a value. The values may be the same between records, but the key cannot be the same. Okay, keys are completely unique within a single collection. Now, let's take a look at the common operations that we will want to do for our table. So, and here they are. So the first one is insert. Insert key value pair. So what does this do? Add a key value pair to the table. That's pretty much it. Put it into the table. And in this case, we assume that the key value pair doesn't already exist. Modify. Modify is similar to insert, except that you're working with a key value pair that is already there. So this modifies a key value pair pair. In other words, a key value pair may already exist within the table, and modify simply updates the value part of the key value pair to something else. You cannot have more than one key value pair with the same key, so modify works with something that is already there, and you're just simply replacing the value component of that thing. So modifies a key value pair. Now, sometimes you may actually take these two functions and combine it into one. So if something is there, put it in, otherwise modify, right? Or sorry, if something is there, modify, otherwise put it in as a new record. So depends on how you write it. So if you say that, I'm going to let the user choose modify or insert, and they should know whether it's new or not, well, that's a different approach. So it depends on how you want to approach your interface, but effectively, those are the two sort of ideas. How exactly you set that up, that's up to you. Now, the third function is remove. Now, remove only is given a key because we actually don't care about the value. We're just saying find the record with this particular key and get rid of it. Removes a record that has a matching key. So in other words, we're basically going through our collection and saying, okay, which record matches, get rid of that one record. The value is irrelevant. The moment you say remove a certain key, the whole record goes away. Search. Search is very important. Search says, find a record given a particular key. So in other words, here is a key. I want you to go find it within the table. So you're searching your collection for a particular key. Now, if this sounds sort of familiar to you, I think I've written something similar to this. Of course, it's actually a very simple idea, um, because we've done like putting something into a collection, like an array. We've done something like remove. The question is not even necessarily about that. The question is, how do you then actually implement this idea? So this is just an abstract idea. This is what a table can do. Now, how are you going to go about implementing this? So at this point, I'd like you to answer that question. How would you implement an abstract a table? What is the underlying data structure you would use? Okay, so take a moment to think about it. Okay, so there was a poll taken, and hopefully you have figured out which one that you want to do. We're going to actually investigate one particular idea. Now, that idea is this. We're going to implement, as our first implementation, a simple method called basically using a sorted array. Create a table using a sorted array. Now, exactly how you implement a table um, has consequences to how fast you can actually do each of these three operations. So the underlying data structure does matter. And by putting in features and so on, you can actually make certain functions faster or slower, depending on what it is that you're implementing. And so depending on your use case, you may say, okay, you know what? I rarely ever insert or modify. So who cares if they're slow? Doesn't matter. I never remove. I know I'm supposed to have that functionality, but I rarely ever do any of these things. I only care about search. Now, if that is the case, then your choice may be to use a certain data structure. And if you say, no, no, all three of these things are really important, then you might use a different data structure. Okay, so the data structure that underlies an abstract data type might actually matter because it depends on what it is that you may wish to do with your particular collection. Okay, so let's start by taking a look at how to implement a table using a sorted array first. Okay, so so in order to use a sorted array, let's be clear on what we mean by this. So we don't actually care about the value. The value is pretty irrelevant to the discussion. Um, so what we really mean when we say sorted array is we're going to use a sorted array based on the key component. So the value is irrelevant. Ignore the value. Okay, the value pretty much whenever we talk about tables is just the thing that happens to be kind of tagging onto the key. We don't actually care about the value at all. So simply take the key and we're going to be using that key for our sorted array. Okay, so when we sort according to the key only. Now, having even said that, I want you to think about how you might actually implement this. So you have a key. Let's say that it's a string and you have a value. Let's say it's an int, okay, for now. Now, does it matter if it's an int or not? Does it matter if it's a string or not? It actually really doesn't matter. As long as you can somehow compare, you're fine, okay? So for our purposes, our keys will be strings, our values will be numbers, okay? But it could be anything, okay? And the table, the way the table works isn't affected by what the keys data type is, nor is it affected by what the values data type is. For our purposes, is string and number. Okay, now let's take a look at how this will actually, how this will actually work. So you have a sorted array that is based on the key component. Okay, now how do you picture this? Okay, so I want you to pause the video here. Think about how are you going to actually do this? How many arrays do you have? That's actually question number one. So um, this is actually two different ways that we can deal with having a sorted array. So we can either take the key value pair and keep them together as one single record, and create an array of records. Okay, we basically create an aggregate type called record, and we keep the key and the value together as a whole. We never separate them. And every single element of the array is a single record. So it's an array of records. The alternative is that we create two parallel arrays. One of them is an array of keys, which is just a string, and one of them is an array of integers. Okay, um, whereas so you have an array of strings and an array of integer, but you keep them parallel. So what do I mean by this? So let's start with the array of records. Let's say that I wanted to start with these two records, cat and the number 1, hat and the number 3. So this will put cat in array 0, okay, sorted alphabetically, and hat with the value 3 in array 1. So that is the record version. We keep the cat and the 1 together as a whole. We keep the hat and the 3 together as a whole, and we put it into each element. Okay? Now, if we were to separate them, then what we do is we put cat into the string array, and we put the number, its associated value 1 into the integer array. Then we have hat in the first one, and we have value in the second one. Okay, the 3 in the second one. So hat and 3 together. Now they are parallel. So what that means is that the keys index 1 and its values index have to match. Okay, you can't have 3 in a different index because then they're not parallel arrays. Okay, so that's what it means to have a parallel array. You have to keep the key value pairs at the same index. Now, let's say that we were to add dog 5 into this list. Okay, where would it go? Well, remember that we are sorting by key, not by value. So dog is alphabetically between hat and cat, right? So if we were to put dog 5 into the record, what we would have to do is we would have to move this one down and then put dog 5 here. Sorry. So dog 5 would end up here. Now, in the other array, we would have to move both hat and the 3 down, so two different arrays have to be modified. And then we would put dog and its value 5 into that spot. So whatever we do to one, in the case of the parallel array, whatever we do to the key array, we have to also do to the value array. It's important that they remain parallel. Okay, so let's say that we did this. Okay, so this is our current implementation. We are implementing this thing as a sorted array. What is the best case runtime of each of the functions that we have? What is the best, what is the fastest that we can implement any of the functions? Okay, so now this is actually the question that you always ask. If you were to implement something a certain way and you have a certain set of functions that you want, how fast would they be? So let's take a look at our four functions: insert, modify, remove, search. Let's start with the easy one. Let's start with actually search. Let's not care about how we got there. Let's start with simply saying, if you have a sorted array, how fast is it to do a search? Now, um, whenever an array is sorted, okay, sorted arrays have the ability to do a binary search. Okay, so if you have an array that is sorted, you can do something called a binary search. Now, what is a binary search? Well, a binary search is so there's two major ways that you can look through a list of items. Okay, so the first is called a linear search. A linear search can be done on any array. There's no preconditions for a linear search. If you're doing something but with a linear search, all you're saying is you're starting at the beginning and you're looking for a value. So you start at the beginning, you say, oh, is this the thing I want? Yes or no. Is this the thing that I want? Yes or no. Is this the thing that I want? And you basically search from the beginning to the end until you find that thing. In fact, this is one of the first algorithms that we analyzed, linear search, right? And we know from experience that linear search has a runtime of ON. Okay, linear search's runtime is ON, where N is number of items in array. Okay, so in order for me to find it, on average is actually, we're going to have to search half the array, but half N is still N. So it's linear in nature, grows linearly as the array grows. Now, um, the other method is called a binary search. Okay, and a binary search effectively uh, uh, has a precondition to it. So first of all, binary search cannot be done if the array is not sorted. So can only be done if array is sorted. Also requires random access to each element. So what does this mean? It means that if you have a sorted linked list, you cannot do a binary search, not on a sorted linked list. And the reason is because it doesn't meet the second requirement of having random access to an element. What is that random access, you say? Well, random access is simply the ability to go to the ith item, so any item given its position, okay, 10th item, 6th item, whatever, the ith item in the list, um, with the same amount of speed, regardless of what I is. So in a linked list, if you want to get to the first item, it's very fast. Front, done. You want to get to the last item, it's also very fast. Back, right? Like that's it. But if you wanted to go somewhere in the middle, that's actually not fast because you have to go through every single node to get to the middle of the array, or sorry, to the middle of the linked list. So you actually have to go through half n nodes to get to the middle. Now, with an array, if you knew how many items are in your array, getting to the middle is really easy. Calculate the middle and calculate the middle index. So you have 10 things, middle is 5, right? Go in. Go to array 5 or 4, okay? But it's simply a mathematical calculation, which is constant. So how quickly you can do a binary search is in order for you to do a binary search, you have to be able to access every single element with exactly the same speed given its position. And because a linked list doesn't have that, you cannot binary search a linked list. It's simply that. So not only must the thing that you search be sorted, it also requires random access. And that second part is often something that people miss. So keep that in mind. You cannot binary search a linked list. Now, um, so how does binary search work? So binary search is like playing a guessing game. So if I wrote down a number right now and I asked, okay, I'm thinking of a number, guess the number somewhere between 1 and 1,000. And you told me 15. And I say, nope. How many guesses would it take for you to find the number that I'm guessing? If my only answer to you was yes, you found the number, or no, you haven't. Well, if you have 1,000 numbers, well, the first time you do it, you started with 1,000 numbers. You made a guess. I said no, and now you have 999 numbers to guess. It's definitely not 15, but who knows what it is, right? So that's the guessing game. And on average, it will take about 500 guesses before you can get the right one, right? Depends on how lucky you are. Now, if it is a binary search, it is equivalent to playing a very different game. So I'm asking you, guess a number between 1 and 1,000. And you say 15, and I say higher. Now, the moment I say higher, what you know is that it's not only not 15, it's also not 0 through 14, right? Like 1 through 14 is also completely, definitely not the answer because I said it was higher than 15, right? Now, 15 was a bad guess because it only eliminated 50 numbers from 1 to 15, right? But if you had guessed 500 instead, and I said higher, well, then that means that it's definitely not only not 500, but it's also not any number smaller than 500. So you eliminate half of what you have. So effectively, what binary search does is the following. It basically says this. Suppose that you have an array and everything is sorted, okay? Everything in the array is sorted. Now, initially, the entire array is available for you. The number that you want to look for can be anywhere in this array, but we know that it is sorted. So what you do is you look in the middle value, okay, so the middle value, whatever this number is, you don't even really care. And you say, okay, this number is X, okay, some number. Now you say, what is the value that's in the middle? And then you say, okay, the number I'm looking for, is it bigger or smaller than this number? Now, the chances of X being the number, 1 in whatever the number the array is. But if I tell you that the number is bigger than X, you can immediately say, oh, okay, you know what? That means that this part over here, this part is never going to be part of my solution. So I can eliminate it. And that's with one guess. Now we then, and it's also not X, right? So we eliminate X as well. Now we then say, okay, let's repeat this process. So what you do is you go into the middle of the remaining section and you say, okay, what is it Y? Is it this number right here? And the answer will be it's higher than Y or it's lower than Y, right? Now, if I tell you that at this point it is actually lower than Y, okay, so what does that mean? Well, that means that it can't be Y, it can't be bigger than Y. So I'm going to eliminate another part of my array. So my whole array, I've actually eliminated 75% with only 2 guesses. Okay, the first guess eliminated 50% of it. The second guess eliminated 50% of what was remaining, which is 25% of the whole thing, right? Approximately. Now that so with simply 2 guesses, I'm down to 25% of the original size of the array, which is pretty significant. And we simply continue this process, always guessing in the middle. So my next guess will be in the middle here, X, Y, Z. And then again, I say below Z or above Z, and we keep eliminating. And this game is a lot faster to play than the original Nope game, right? So effectively, it's two number guessing games, and one of which is eliminating half your search space every time, and the other one eliminates one value of the search space at a time. That's why. Okay, so that is what binary search is. It's basically a different way of searching. You can't do it if it's not sorted. You can't do it if there's no random access. Okay, but that's binary search. Now, what is the runtime of binary search? Well, the runtime of binary search is log n. And it's log n because every single time we do this, we actually eliminate half of our search space. The full analysis is available in the course notes, but for now, just trust me and say this is log n. Okay? So this is how sorted arrays work, linear, and so the sorted arrays, and with sorted arrays, you can do binary search. You don't have to do linear search. Now, what that means is that of the four functions that I have, what I can say about searching is that this is doable in O log n time for my, so these are my four functions. So given, sorry, this is not for general. So my search function using sorted arrays is O log n. Okay, search is log n. That's good. Like that is actually fast. By the way, log n is fast. The only thing faster than log n is constant. Okay, so if you see log n, you should say, yes, that's great. That's amazing. Log n, awesome. Okay, so log n is great. Log n is a good search. It's a good speed. Leave it. Okay, perfectly happy with log n. Now, how fast is it for us to do then, instead of log n, how fast is it for us to do a remove? What is the runtime of removing a record from this list? Now, we have to keep the list sorted, right? So when we remove something, we remove according to a particular key. So when we're removing according to a key, we have to find the key. That part we can do in log n, okay, because we can searching for it is log n, right? So if we were to call remove and it includes the searching component, then doing the search part is log n for the search, plus we have to do the removal. Now, let's say that I was trying to remove cat. Finding cat is log n in my in my diagram here. Okay, finding the cat, that part is log n. Getting rid of it, though, is not log n, because what we have to do is we have to shuffle everything up. So if we were getting rid of cat, okay, it's more than just this. That part's the easy part. The hard part is at this point we actually have to move everything up. So each record has to get moved. And over here, similarly, every single value has to be moved up. Now you say, well, but cat was the first one, right? What are the chances? What if it's somewhere in the middle? Well, then you have to move half the array. On average, you're moving half the array, right? Because on average, you could be anywhere within the array. So on average, you have to move half of it. But remember, half n is still n, right? That's the weird, big O math, right? Half of n is n, quarter of n is still n, right? It doesn't matter what the constant is. So half n is n. And because of that, actual removal um, is ON. So the removing process will cost you ON. Okay. Now, what about inserting something new? Inserting a key value pair. What's the cost? Well, we have to figure out where to put it first. Okay. Now, figuring out where to put it can be done as part of the insertion process. Um, and it's probably actually faster that way than to, because you have to do the moving anyways. So let's say that I wanted to put cat back into my array. Okay, what is the fastest way to do this? What is the fastest way to put cat back into the array? Well, there's different ways, by the way. The first one way is you can do a binary search to kind of look for the position, and then if you find it, great, and if you don't find it, then um, sorry, you look for the position using a binary search, and then the position where it is, okay, um, will where it should be, you can have the binary, you can alter the binary search to return that. So you return the location of where it would be if it was actually there, as opposed to where it actually is, right? And there's ways that you can code binary search to actually do that. Now, let's say that but the better way is actually to simply put it in by taking a look at whether or not you can put it in at a certain position. So if you know that it's not there already, if you know that cat isn't there, or you know its position, um, all you have to do the insertion, now this assumes that you know that it's not there, okay, is simply go through your list and say, okay, can I put cat right at the end here? Is this spot the right place for cat? And all I have to do that is to look at the one right before it. And if cat is bigger than that one, I put it in. Now, cat isn't bigger than that, so what I have to do is I have to move this record down. Take this record, move it down. And then this is the available spot, and I say, can I put cat there? And the answer is still no, so I again move the dog and 5 record down. And now that I'm at the beginning of the array, this is the only spot left for it. So I will put cat in. So cat 1 goes here. Same process for the other one. You just have to deal with 2 different arrays. Look for where cat should go, moving each record in parallel. So move these guys in parallel. Don't ever separate them. Okay. And then put in your cat. Okay. So this is, oops, I think I got rid of the 5. Sorry, that was accidental. Now, in any case, that is pretty much how you can insert. You basically figure out whether or not something is there. So if you separately call insert and modify, so if there are 2 separate functions, insert is only ever called if you know the data is already not there. Then the process is simply move everything as you go and then do the insertion. Now, if you don't know if it's there or not, then you have to do a search first to figure out if it's there. Okay, so there's pluses and minuses, but either way, what you're doing is you're just moving things along, okay, until you figure out where the opening should be and then put the record in. What is the cost of this insertion process? The cost is actually relatively inexpensive. Well, I guess maybe not, depends on what n is, right? The cost is on, okay? Now, on is not super bad, but it's also not super good. If n gets big enough, on is slow, okay? So keep that in mind. It depends on how big n gets, okay? So the smaller, so sometimes these things are actually important. Like, what is n, right? Like, if n is 20, who cares? Okay, a computer can handle that fairly quickly. If n is bigger than that, then it becomes it's actually important. Um, so keep that in mind, but effectively, that's what it is. Okay, so insert, and then we have modify, or sorry, modify. Now, modify key value pair is similar to insert, except that it works on something that is already there. Figuring out where it is, that's just a search. Okay, so this one is O log n to find the record. And then the actual modification. Now remember, modification is simply updating the key value pair, right? modification itself is actually O1. It only costs us constant time to write the value into the place. So if I was to, so that's pretty much what modify will cost us. Okay, so that is pretty much how a sorted array would work. Okay, so here is a question for you. So this is a sorted array implementation of a table. We've talked about how you can do a how you can do a binary search to make search faster, remove, insert, and so on. So here is my question to you. Okay, how fast? What about an unsorted array? What is the speed at which you can search, insert, remove, modify? Okay, so search, insert, remove, and modify. Now, we're going to assume, okay, that effectively the search will be search a search. Okay, how fast can you put something into an unsorted array? Okay, now it assumes that you know that nothing is there. You assume that the item isn't there. You know that it's not there. Okay. Now, how do you know? Well, you might actually have to do a search first. Okay. So keep that in mind. So if you don't know anything about your data and you have to actually check whether or not you can do something quickly, then that then you'd have to actually account for that search cost. Okay, so here is the question: how fast do you think each of those are if the array was unsorted? So pause the video, put up a poll, and tell me what each of them are. Okay, so search. How fast is search? Let's start with that. Okay, so for a search function, an unsorted array is actually going to cost you ON because it's unsorted. You can't do a binary search. So any searching of an unsorted array will cost you ON. Now, usually in a table situation, searching is actually the most important function because you typically search a lot more than you insert or remove. And because of this, this is actually a worse implementation already, simply because searching is much more prevalent than the other ones. Now you say, oh no, I'm just going to insert and remove things, right? That actually doesn't usually happen, okay? So most of the time tables are built to be searched, okay? So you might actually insert only enough to get all the data in, and then you search forever after that. Like search happens way more than insert, remove, or modify. So keep that in mind that this is probably already bad simply because of this. Okay, so what do you think the runtime of insert is? Assuming that you already know it's not there. So assume that you've already taken into account of the search cost. What is insert going to cost? The answer is actually it's constant because we already know it's not there, right? So putting something in, where do we put it? Just put it at the back, right? And now we know exactly where it is. It's right at the back, done. Very easy to put in. Don't have to move anything around. Okay, what about remove? Okay, go ahead. Put in your guesses for removing from an unsorted array. Go. Okay. Now, for remove, the answer is it's going to be ON. Now it's ON for searching for the thing you want to remove, and ON also for removing. Because even though the list is not sorted, the thing that you remove might be in the middle of the array. So you can't just like leave an empty spot somewhere in the middle of the array. You actually have to still push everything back up. So because of that, that's going to cost you ON. So the whole thing is ON. Okay. Now, even if you say, you know what, I'm going to leave an empty spot. I'm going to, be a rebel. I'm just going to leave it empty. And if you're searching for something, you see an empty spot, you just ignore it and keep going. That's fine. Okay. Your search is still ON. So the whole thing is still ON. Okay. What about modify? Last one. How fast is it to modify a key value pair? Okay, the answer for this is it's ON because it's going to cost you ON for the search. And it doesn't matter that the modification part, actual modification, is still O1, but the whole thing is still going to cost you ON for the total. Whenever you have an algorithm, any operation that has two distinct steps, so like this one, search, remove, search, modify, the um, the cost is whichever is more expensive. Okay, so if you have step one, step two, step three, step four, whichever one is most expensive of each of the steps, assuming that they're completely independent. So in other words, what that means is step one does not make step two cost more ever, no matter what the return value is. Step two will never make step three cost more, whatever the return value is. Um, if this is the case, okay, completely uh, three or four, like a whole bunch of completely independent steps, then the cost is whichever is the most expensive. Excuse me. Sorry. I don't want to remake this video, so I'm going to keep that in. Okay. So, anyhow, it's ON in total. Um, and so you're always catching the most expensive step. All right, that's actually everything. So in the next set of videos, we're going to start talking about something called a hash table. The recap actually does a pretty decent job of talking about hash tables already, so I'm not going to redo that. Keep in mind that any talk about assignments in the upcoming videos has nothing to do with your assignment because that was made for previous semester. Okay, the material itself is still exactly the same, so I'm not going to remake the videos, but just keep in mind to ignore any talk about assignments. Okay, thank you everybody. Bye bye.